Okay, in this video, I'm going to be talking about homogeneous differential equations. And they're defined as equations of the form y prime, the rate of change of y, is equal to some function f of the ratio y over x. Now, first off, note that this has nothing to do with linear homogeneous differential equations, right? The ones where we have y prime plus p of x, y is equal to 0, right? The right-hand side is 0. This has nothing to do with those type of homogeneous. It's a completely different use of the word homogeneous. In fact, it's actually related to homogeneous functions, which again is an entirely separate concept that you don't really need to know. Just know that homogeneous differential equations are different than linear homogeneous differential equations. Also, this definition here is a little bit abstract. One example of a homogeneous differential equation would be y prime is 2y squared over x squared, right? Because this can be written as 2 times y over x all squared. And so you can see y prime is just dependent on some function of the ratio of y over x. Okay, so how do we solve these types of equations? And we can do this using substitution. If we let u, a new variable, to be the ratio y over x, well, that kind of makes sense because then the right side of the equation just becomes f of u. But then if we write this out, right, multiply by x on both sides, we get u of x is equal to y. And that means if we take the derivative of both sides, on the left-hand side, we use the product rule. So we're taking the derivative with respect to x. On the left-hand side, we get derivative u prime times x plus u times the derivative of x with respect to x, which is 1. And on the right-hand side, we get y prime. And so now you can see, filling in right here, y prime is equal to u prime x plus u. So you can see u prime x plus u. Now at first glance, this new equation doesn't seem to be any simpler. But in fact, if we isolate u prime, I'll do it off to the side here. If we isolate u prime, we get f of u minus u all over x, which is, right, we can rewrite as f u minus u times 1 over x. In other words, this is a function of u only times a function of x only. And so this is actually a separable differential equation. And so if I rewrite this, I use Leibniz notation, du dx times x plus u is equal to f of u. And then I move all the u terms to the left-hand side and the x terms to the right-hand side. I'm going to end up with, so let's see here, du over dx times x is equal to f of u minus u. And then so I get 1 over f of u minus u times du is equal to 1 over x times dx. And now, of course, we can integrate both sides. And on the right-hand side, we get the natural log of x, absolute value of x, in the most general case, plus an arbitrary constant. And on the left-hand side, we have some integral, right? Maybe, who knows? Hopefully this integral is solvable, but it'll be some function of u, right? This whole integral, this whole antiderivative will be some function of u. And once we do that, on the left-hand side, we'll have some function of u. We can make that substitution, u equals y over x, back in to get a solution in terms of y and x, and then this may or may not lead to an explicit solution. At least we'll get an implicit solution, right? And then we may or may not be able to solve directly for y. Okay, so to recap here, homogeneous differential equations are equations where you can isolate y prime and write it as a function of the ratio y over x. And when we encounter this case, we make a substitution, u to be y over x. And when we do that, we get this for y prime, which turns it into a differential equation only in terms of u, right? F of u is equal to u prime x plus u, and in which we can rearrange, it's separable, and we can solve for u, and then hopefully plug that back in, u equals to y over x, and then see if we can find a solution for y.